Welcome back. I hope you had a nice break, and it's now time to go to Manchester, where Dr. Ed Pickering and Dr. Aneeqa Kahn are going to talk about materials for fusion power.
Thank you very much, Chris. Can you hear me okay?
Yes, I can.
Brilliant. I think my video was turned off, so could I just have it turned back on again? I think the host might have to do that. I don't know whether that's you, Chris. Oh, brilliant, yeah. Cool, and Aneeqa's here with me, so. Right, I'm going to try and share my PowerPoint and put it in presentation mode. Does that look okay? Can you see the presentation mode? Okay.
It's in the next slide mode.
Oh, is it? Wait, swap this. Let me just swap the displays. Is that better?
Yeah.
Cool, brilliant. So yeah, Aneeqa, do you want to start us off?
Yeah, hi everyone. Welcome to our talk on materials for nuclear fusion. I'm Dr. Aneeqa Kahn, based in Mechanical Aerospace and Civil Engineering at Manchester, and I'm joined with Ed. Yes,
so I'm Dr. Pickering. I'm based in the Department of Materials at the University of Manchester, and I'm also part of the Henry Royce Institute as well. And we both study materials for nuclear fusion, and this is what we're going to talk about today. So I'm going to start off with the first few slides, just give us some background as to the problem that we're trying to solve with fusion power. Let me just, I think I've just got to move a couple of Zoom windows out of the way. Okay, so the problem that we have at the moment is that if we look globally, 80% of our energy comes from fossil fuels. So if you look at the total global energy supply that we've got in the world at the moment, we can see that coal, natural gas and oil, they're all increasing the amount of the amounts that we use of those, and they predominate over carbon-free sources of energy like nuclear. Biofuels and waste, you can argue whether that's carbon-free or not, and then these two bits here are the true renewable sources of energy. So really a tiny fraction of the total energy that we use in total in the world. And the problem is a little bit better, but still not great in the UK. So this is the total UK energy supply, and we can see that as we've progressed through the 2000s, the amount of energy that we've used in the UK has decreased. That's because we've become more efficient at insulating things, or we've adopted things like LED light bulbs, that sort of thing. And it means we've actually nearly totally eliminated coal, but still we burn a huge amount of natural gas and oil. And yeah, a lot of this, and I've just highlighted natural gas here, is actually probably, well, in the wintertime, over half of this of the total energy we use is for heating our offices, workspaces, and providing other sorts of heat in industry. And most of that is derived from burning natural gas. So that's why I've highlighted that there. Okay. So what's the solution? Well, we need to stop burning fossil fuels for transport and for heating, because that's where all those fossil fuels are used mainly at the moment. Okay, and we need to move to electricity instead for our transport and for our heating. It means we need more carbon-free electricity generation. So if we're going to use electricity in our cars and to heat our homes, we need more electricity, we need it to be carbon-free. And renewables continue to be a massive part of this, and we're investing massively in new renewables in the UK, but we also need lots of power that's not weather dependent. In other words, that's weather independent. I'll just illustrate the problem here. So this is just looking at the energy supplies from this is the electricity supply, okay, so not the total energy, but just the electricity supply to our homes and businesses on Sunday. And it was a pretty windy day, so you can see here the wind accounts for 33% of our electricity, and we burnt a little bit of gas and no coal at all, which is this grey bit at the top. You've got nuclear on the bottom here. But when the wind doesn't blow, unfortunately, what we have to do is we fill that gap with coal and with gas, and that's not a good thing. So we need more clean electricity power generation, okay? Particularly if we're going to use more of it to heat our homes and fuel our cars, okay? So is nuclear fusion the answer? Well, that's what we're going to discuss now. And in particular, we're going to look at the materials challenges for nuclear fusion, because they are a critical issue to commercializing it.
Okay, so I'm going to just mention what nuclear fusion is. So it's what it says on the tin. You're fusing things together in nuclear fusion, and it's the same process that happens within the center of the sun. So that's where all the energy from the sun comes from, fusion reactions. On Earth, the most efficient fusion reaction that we intend to use for commercial energy production is the reaction between two isotopes of hydrogen called deuterium and tritium. And we've chosen this reaction because the cross-section, or the likelihood of the reaction, is around 100 times greater than other fusion reactions within a similar energy range. When we react or fuse together the deuterium and tritium, we get some helium, which you can see in this reaction at the bottom, and also a highly energetic neutron with 14 MeV. And the energy of these neutrons is much higher than in current nuclear reactors, which are powered by fission or splitting of atoms rather than fusing them together, which provides kind of unique challenges to this fusion method. I'm now going to talk a bit about the ITER project. So the ITER project is an international collaboration between 7 partners. So the European Union, the US, Japan, Korea, China, India, and Russia. And it's based in the south of France. And it's somewhere where they're trying to build the largest fusion reactor in the world and explore some of the materials challenges that we might have to face. So just for a bit of a scale for the size of the reactor. So the reactor is something called a tokamak, which is a large donut-shaped device where the reaction takes place in this kind of area here where Ed is highlighting his mouse. And so the radius of the tokamak is around 6 meters, and the whole device is almost 30 meters in diameter and height. And you can see the little person in the bottom right-hand corner, just for a sense of scale on how big this reactor is. So it's a huge engineering challenge and a huge materials challenge. So I'm now going to talk about the specific materials issues that we might face in a reactor like ITER or in other types of fusion reactors. So the first big issue is what I mentioned previously, is that we have these really energetic neutrons, 14 MeV. And I'm going to go into these in a bit more detail in the next slides, but here I'm just giving a bit of an overview. You also have very intense high heat loads. So the center of the plasma, which is where your reaction is taking place within this tokamak. So a plasma is an ionized gas, which is what happens when you get to very high temperatures. And in a tokamak, the temperature at the center of the plasma is almost 10 times hotter than the center of the sun. So very high heat loads. On top of that, we've decided within the fusion community, we don't want to have a lot of radioactive waste after we do these reactions. So we choose to use materials that are reduced activation and won't be producing a lot of high level radioactive waste at the end of life of the reactor. We also have the helium that's produced in the reaction, which can interact with your materials and cause a lot of different kind of effects within that. And then on top of that, as I mentioned before, we have the plasma, which also interacts with the materials that are on the walls and sides of the reactor too. And to confine this plasma, one of the techniques we use is high magnetic fields. So we have materials challenges in generating those magnetic fields, and then also what is the influence of such high magnetic fields on the other materials in the reactor themselves. So I'm now going to talk a bit more about the 14 MeV neutrons and what kind of damage they induce. So if you imagine a neutron like a snooker ball hitting other snooker balls, it generates a kind of cascade effect. So the neutrons will hit atoms within your material, which will then hit other atoms, and it will just keep going further and further and further, generating a lot of different types of damage, which are displayed in this diagram here. And this varies across time scale and length scale, depending on what the damage is. And one of the big challenges for us as material scientists is trying to predict what this damage will be and choose materials that can cope with this damage. We don't have a 14 MeV neutron source that we can use to test all of these materials. So often we use other techniques such as ion irradiations. So if you imagine the neutron hits atoms, which hits other atoms, we kind of bypass the neutron and just implant other ions into the sample, which hit the atoms as well and generate the same kind of cascade. And we could do that with protons as well. And we try and correlate that to neutron damage. And we also do a lot of different types of modeling as well to predict behavior. But it's a really huge challenge. And those tiny defects, whether they're vacancies or very small scale generation of helium, etc. When you get to the larger scale, they can really influence the mechanical properties of your material and the engineering properties of the material. So it's really important we look at this. So as I mentioned, there's very high heat loads, and I really like this slide because it puts everything into context. So on the left-hand side, we have a HWR, a nuclear reactor, a re-entry vehicle, a Rolls-Royce engine, and all of these kind of 3 examples still have lower heat loads than the steady state operation heat loads on the diverter, which is shown in the bottom middle of this as well. So that is kind of an exhaust for a fusion reactor, which I'll talk about a bit later on. But even during normal operations, the heat loads that it's facing are much lower than those other really extreme examples. And then on top of that, we can have events called transient events, which are on the right-hand side of this slide here. And those would face heat loads even higher than a rocket or arc welding. So really extreme heat loads experienced within a fusion reactor, which is something else we also need to consider.
Yeah, I'm just going to briefly talk about the reduced activation that Aneeqa mentioned before. So this is the idea that in order to be a safe and environmentally friendly source of power, nuclear fusion needs to use elements or materials made from elements that are reduced activation, which is to say when they're hit with high energy neutrons, they don't become radioactive. Okay, so this is a really interesting periodic table that basically shades the elements according to according to how long they will stay radioactive after being subject to a to being a part of a fusion reactor. So these are modeling results because obviously we don't have a fusion reactor yet to test this. But what you can see here is that elements that we might commonly use for a material are in red, and that means they're going to be radioactive for a long time. Okay, but it's interesting to note that this is for one part of a fusion reactor. This is the first wall. That's the first thing that a plasma would hit in a tokamak. If we go to a different region, okay, so this is the blanket shield that's behind the first wall, then maybe there is less activation, but there are still certain elements we need to avoid, and there are certain elements that we like. So for instance, tungsten that we do use in the diverter, as we'll discuss in a second, that is an element that decays to a safe level in not very long time. So that's a good element to use.
So now I'm going to talk a bit about the influence of helium with materials in the reactor. So as Ed mentioned, tungsten is one of the candidate materials in the diverter, and this creates a lot of interesting effects when it interacts with the helium. So at lower temperatures, you get kind of nanobubbles produced in your material at 600 to 700 Kelvin. However, at 900 to 1900 Kelvin, you get this phenomena called fuzz, which is like a nanostructure that forms on the surface of your tungsten. And it actually turns the tungsten black. So when you look at it with your eye, the whole surface of the metal has turned black. And so it's the darkest man-made metal ever, which is very cool. So although generating such kind of defects within a fusion reactor might be problematic if the fuzz fell off or produced dust within the reactor, it might, cause erode and things like that. Due to its unique properties, it might have beneficial impacts in other industries, which is something that I think is very interesting about material science. So when something might be problematic for one industry, like the fusion industry, it might be useful for other things. So this fuzz is being explored for photocatalysis, also for like solar panels, gas sensors and things like that. So it could actually prove quite useful in other industries. And then at really high temperatures, you get things like large voids on the surface of your tungsten as well. And all of these surface modifications then can influence the thermal properties of your tungsten, the mechanical properties, and also fuel retention. So as I mentioned before, one of the fuels we use is tritium. And it's really important that we don't keep that stuck inside the materials we're using. There's only a limited amount of tritium in the world at the moment, and we don't want to have it stuck in places where it shouldn't be. So that's also somewhere that we have to look at.
Absolutely. So yeah, in terms of the plasma itself, so obviously it's exceptionally hot, as Aneeqa mentioned. Fortunately, the operating material temperatures, the materials that are only a few centimeters away from the plasma are significantly below that. So they're a couple of thousand degrees C maybe, rather than 100 million degrees C. So that's good because it's nicely confined by the magnetic field. But plasma interactions with the material can still have, it can be very damaging and detrimental. So we can get physical erosion of the material. Material can be picked up and then deposited elsewhere. That can form deposition. We can get dust from different areas of the reactor. As Aneeqa mentioned, we can get fuel retention. So this is when the tritium essentially becomes embedded in our materials, makes them radioactive, and we lose that tritium. And it can also lead to the generation of bubbles, blisters, and general embrittlement of the material. So that's just a general, making the materials more brittle, and that's not good for obviously the structural integrity of the reactor.
Okay, so as I mentioned, the magnetic fields that we need to generate to contain that plasma are very high. So for an example, for ITER, we need magnetic fields of 13 Tesla to confine that reaction. So for example, you can compare that to a PET scanner in a hospital, which is typically only 1.5 Tesla, which we would normally consider quite high. So imagine, 13 is huge. So the first materials challenge is generating those magnetic fields. So there's kind of two main pathways that are being used at the moment. So in ITER, they have supercooled, superconducting magnets that they're using to confine this magnetic field. So they are cooled to temperatures of almost absolute zero. And actually, this is one of the fun facts about ITER that I really like, that you have those supercooled, superconducting magnets at almost absolute zero. And then only a few meters away in the center of the plasma, you have temperatures 10 times hotter than the sun. And nowhere else, in the universe do we have such an extreme temperature gradient. So that really also kind of highlights the extreme challenges that material scientists face in a fusion reactor. However, another technique that is being explored to generate those magnetic fields is high temperature superconductors. And the benefit of those is that you can actually build a much smaller reactor, which might be useful in the future. So we've got companies like Tokamak Energy and also the Spark reactor in the US who are looking at these high temperature superconductors for building fusion reactors. So on top of the materials challenge of generating those magnetic fields, it's also important to look at the impact of those magnetic fields on other materials within the reactor as well. So that's also something material scientists are looking at.
Great. So essentially, I'm just going to give you an overview in the penultimate slide here of the various materials that are currently being used or are proposed for use in ITER. Okay, some of these materials will change in later commercial power plants. So they're certainly not the #1 choice at the moment, but they are the choice for ITER being an experimental reactor. So firstly, we've got in green there around the whole reactor, we've got the cryostat. So this essentially is help hold the coolant for the magnetic or superconducting magnets. So that's what's called the cryostat. It's essentially a big fridge, and that'll be made out of stainless steel. So a very common material that we know very well how to use. Again, for the vacuum vessel, so the plasma chamber itself is kept under an exceptionally high vacuum. It's a very, very clean environment, it should be. And this is made out of stainless steel, that vacuum vessel, which is the sort of the C shape there in yellow, but actually that goes all the way around and forms sort of the shell of the donut, if you like. Aneeqa mentioned the diverter, which is essentially where all the exhaust gas from the reactor that's where it goes. So any pollutants or any sort of materials that happen to enter the plasma, they can get directed down there so that the plasma continues to react very cleanly. Okay, and we use tungsten there because that's a very high melting point material. For the blanket, we're using beryllium for ITER, but this is actually a toxic material and may not be used in later reactors. And that's used basically because it's quite easy to spray onto the outside of the blanket there. Actually, this is the first wall section of the blanket that's formed of beryllium, and it doesn't cause significant damage to the plasma, to the integrity of the plasma, if it happens to be eroded and falls into the plasma, whereas something like tungsten would, because it's a much bigger atom. And then for the magnets, we use sort of niobium tin or niobium titanium based superconducting materials there. Okay, so that's sort of the blue. So we have a core, and then we also have actually coils around the donut, the shape of the donut as well.
Okay, so in summary, we need to have much more carbon-free power generation, and nuclear fusion would be the ultimate weather-independent power source if we're able to crack it. The conditions inside a nuclear reactor are very harsh, as we have shown in this talk, across a wide range of conditions. And we need to consider special materials that can withstand the neutron irradiation at 14 MeV, the extremely high heat loads, helium exposure, plasma interactions, and also the very high magnetic fields as well.
Yeah, good. So yeah, I hope you found that interesting, and I think we might have a few questions, Aneeqa. Let me just have a look.
Thanks very much for that. It was great.